Welcome to the third and final part of Chapter 7, covering the Solow growth model. Now, last few lectures really, we've solved out the Solow model, and we talked about some interesting stuff with it, but now it's time to apply it to some real-world stuff, sort of real-world stuff, really talk about some critiques of the model, how it holds up, how well it actually predicts things, and also fit it to an example for, knowing how to do stuff for an exam. So we can look at savings rates across different countries. We can look at how they grow, look at how much capital each country has, and we can hopefully use the Solow model to predict how they'll grow. Question: is there really any chance two countries with different savings rates and capital endowments could eventually converge in growth with one another? Now, the Solow model says yes, but it's conditional on how much each country saves. A rich country could theoretically stop saving as much and slow in their growth, while a poor country can save up a lot and speed up in growth. All right, it's kind of like the story of the tortoise and the hare. If you remember that when we were kids, all right, there's the turtle, the tortoise, the hare is a rabbit, and they decide to race for some reason. And the hare is like super confident that he's going to win the race. So when the race starts, he ends up dragging his feet. Meanwhile, the tortoise is really slow, but never really stopped trying. Slow and steady wins the race. He eventually catches up with the hare and wins. You can kind of think of this as the same idea in terms of like economic growth. So suppose we can start really with any two economies with a positive initial capital stock and a similar alpha. Remember, alpha is the capital's share of income. And the question would be, will they go to the same steady state? Now, if there were differences, these differences do have to be measurable, right? Now, we don't have any functions that aren't measurable in the real world, so we're in good shape here. We have two different economies with different positive initial capital stocks. So their interest rates could be different. Incomes would obviously be different. And we know for a fact, since the marginal products of capital are diminishing, and they're also different in this case, that interest rates should also be a little different. But do countries differ only because of differences in marginal product of capital, holdings of capital, or the population? Well, kind of, sort of, yeah. Solow himself described differences in countries at the cross-sectional level. Now, what's pretty awesome about this is while it wasn't like, the best thing that's ever been done, it is impressive the headway he made with so little data. And really, I mean, there's some genius to the way the guy thinks on that, but there are some endogenous differences. So while the initial model may have said one thing, reality and more complicated models gave us a bit of a different story later on. But hey, we all got to start out somewhere, right? And so Solow himself didn't develop this model until like 1956, which was something like 180 years after Adam Smith. And so, I mean, really, if you think about it, it took a very long time for economists to develop enough math to be able to use it in a way that was needed. Now, let's back up a little bit to Adam Smith. So he published The Wealth of Nations in March of 1776, and this is really, one of the first major works in classical economics. And he talked about a lot of things, like how nations can build wealth, talked about economic growth and development, things like division of labor, use of money, wages paid to labor, use of resources, and differences in economic growth between nations. Now, he got a lot right, but he also got a lot wrong. Then we had guys, it's kind of a little bit of a segue here, but what the hell. Robert Thomas Malthus did some pretty influential stuff. What he argued was that population growth was exponential, but the growth of resources, the food supply, things like that, was linear. And eventually we'd run out of resources, trigger population decline. It's what's known as a Malthusian trap. Now, if you ever hear any conspiracy theory stuff about population control and all that, it's generally based in some kind of theory related to the work of Malthus. Now, unfortunately, what happened is Malthus died before he could see the demographic technological changes that took place to show him that his ideas would become wrong. Now, I want you guys to think about how and why he would have been proven wrong. Think about it in terms of the Solow model, right? Think about this really, the interesting thing, the crux of the argument for why he's wrong would be the linear growth of resources. Like, Essentially, think about that as technology. Does technology play a role in how efficiently we can use various resources? And then think about how the Solow model in that context could be proving Malthus wrong. Now, it's not for a grade or anything. Just kind of think about it on your own. Now, let's fast forward like a lot, and we get to Robert Solow. Now, the model that he developed was meant to show us how countries grow from things like savings, capital accumulation, and the role technological change plays in it. And he argued that technical progress contributed mostly to growth, and it wasn't, in fact, capital accumulation that contributed to growth. And the data exercise I was talking about a few slides ago used data in the U.S. from 1909 to 1949. And he estimated it with observables like capital, labor, stuff like that, and treated the difference between estimated output and observed output as technological progress. This is what was known as the Solow residual. And the Solow residual suggested that almost 86% of output growth was the result of technology, and the remaining balance was due to capital, which is a pretty inflated number. It doesn't really make a whole lot of sense. However, Solow himself was even a little elusive as to what quote-unquote technological change even was. So let's take a short little detour here, talk about what that Solow residual is. Solow's idea was, let's say you've got some function given by y equals alpha times x plus epsilon. You're modeling y as a function of a set of observables, call it x, and then what can't be explained by the data, which is that epsilon. Right? So if you're modeling something and you try to say 86% of whatever it is you're modeling is explained by stuff that you can't observe, right? Thus 86%, epsilon's 86% of what's generating y. Well, you're probably not going to have a very good model. And Solow essentially argued anything that shifted the production function either up or down, even just a little bit, was technological change. And naturally, with a number as high as 86%, some researchers came in, they wanted to look at it a little bit. And their idea was maybe there was like some trend cycle stuff that was really being improperly measured. Is he confusing short and long run behaviors in such a way that maybe they're kind of playing a role in ways that they shouldn't be? So in that sense, maybe, the model wasn't really the best for what Solow initially thought it was good for. Now, researchers, as they stepped in and got pretty critical of that Solow residual, they started calling it a measure of ignorance in the modeling. And the idea is that there was a measurement problem in accounting for these inputs and what technical progress even was. Solow said it was anything that shifted the production function up or down. Now, there were a few papers that came out to refute the idea of the Solow residual, and one of them found something like 97% of total output growth was actually explained by the inputs and not by the Solow residual. And the paper thus reduced the role that total factor productivity, or the Solow residual, played in output growth over time, and instead argued a lot of growth came from endogenous variables like capital. And a lot of this led to the birth of like the neoclassical growth model, the endogenous growth model, things like that, and the inclusion of individual optimizing households in the model, which, if you remember, Solow didn't do, right? Solow assumed households existed, but he didn't really assume that there was any explicit modeling for the households part. The households themselves weren't making any decisions in the model that would be affecting the way the model, developed over time. So let's cut through an example here. We've got two countries, right? Turkestan and Turkestan. And I promise one of these days I'm going to show you where I got these ideas for the names. But let's just say for now, right, they're neighboring countries. And the idea here is, can these two countries with potentially different initial endowments have the same steady states? Well, we got to play around with some math to really find out. Now, let's say they all start with the same endowments of capital, the same labor, and they have the same depreciation rate, delta. However, investment for Turkestan is 1,000, and investment for Turkestan is 2,000. So they've got initial endowments, but one is investing more than the other. Now, while we've got that one difference, they do have another similarity, and that output is characterized for both countries by y equals a times k to the 1/3 times l to the 2/3. So with all that, what are the savings rates for each country? Well, fortunately, we do have enough data to figure out what the savings rates are. We just need to remember what relationships there are that are going to allow us to get the savings rate. Because remember, they've got the same initial endowment, but they have different investment rates. So savings rates are going to have to be different because of the differences in investment, right? If you're investing, you're saving. The amount that you're investing is the amount that you're saving. So if they've got different amounts of investment, they're probably going to have different savings rates. So if investments equal to savings, then the savings rate will have to be equal to the ratio of total savings to total output. So fortunately, yeah, we've got all the inputs we need to get this. So first what we need is we need output. Now output for both countries is the same in the first period. So we plug in everything we need. We let A be equal to 1 for now. We get 10,626.59 as output for both countries in the first year. So we can do this a number of ways, but what I'm going to do is I'm going to invoke the relationship that investment equals savings. So S times Y equals I. So for the first country, Turkestan, I just take investment and I divide it by output, and that gives me the savings rate, right? So I just plug and play. 1,000 divided by 10,626.59 gives me a savings rate of 9.4%. What about the other country? What about Turkestan? Well, for Turkestan, they're saving a little bit more, right? They're saving twice the amount. So their savings rate is probably going to be twice the amount. So we plug and play, we get 18.82% for Turkestan. So they've got different savings rates in the first year. So even though they've got the same output in the first year, if they have different savings rates, output in the next year is probably going to be a little different. So what are the outputs in each country in the next year? Well, what we do is we just shift everything up one period. All right, this is where we really need to be able to use the depreciation rates for these countries. So we recall the equation for investment, which is the law of motion, right? Investment equals tomorrow's capital minus today's capital less depreciation. So starting off with Turkestan, right, we know what investment is. We know what the first year's capital stock is. And from there, we can figure out what next year's capital stock is going to be. All right, investment's equal to 1,000. We don't know what next year's capital stock is yet, but we do know 1 minus delta is 0.95 because delta is 0.05. So 1 minus 0.05 is 0.95 times 12,000, which is the initial capital stock. So tomorrow's capital stock, or next year's really, is 12,400 units of capital. All right, what about the other country? What about Turkestan? Well, it's now 2,000 for investment rather than 1,000. So KT plus 1 minus 0.95 times 12,000, I get 13,400. Now, since labor doesn't grow, right, L stays the same. And here we get to see how much each country's output's going to increase, conditional on just how much they're saving, thus how much capital itself is changing. Now, I'm going to shift everything sort of like up one period or whatever. So YT is really YT plus 1, but it's like, well, okay, now we're in today rather than yesterday, looking tomorrow, all that stuff. So the subscripts for time are going to be the same. And for Turkestan, I get 10,743.37. For the other country, for Turkestan, I get 11,024.74. So we can already see they started at the same point, but because they're saving different amounts, even just one period ahead, their output is now different. So from the answer to the previous question, right, what happens when one country saves more? How would this be related to steady state output? Well, if a country saves more, we can see that they'll have higher outputs just simply because of the relationship given by steady state output, right? Steady state output is S times A over delta times alpha over 1 minus, to the power of alpha over 1 minus alpha. So every term in that function is positive, namely in the numerator, especially, well, it's positive everywhere, but in the numerator, right, S is there, S is positive. If S increases, if the savings rate increases, steady state capital increases, thus steady state output increases. So if you save more, you'll have higher steady state output. All right, another question here. Suppose Turkestan's got a technology shock where A is equal to 1.5. Now, Chirpistan does not have this technology shock. What happens to output? Well, for Chirpistan, it stays the same. Durpistan, on the other hand, right, we have, 11,024.74. So what I do is I just take output for Durpistan and I multiply it by 1.5, and I get 16,537.11. So that would be if they get a technology shock, it increases their output by 5,500 something units of output. Now, cool. Next question. Suppose both countries don't have equal endowments. Suppose Chirpistan has initial endowment of K equals 1,000. Durpistan has initial endowment of K equals 800. The question here would be, what conditions would be required for both countries to converge to the same steady state? So recall the equation for per capita steady state capital is S times A over delta to the power of 1 over 1 minus alpha. Now, with this equation, we don't even need the different amounts of capital, right? Because we know that delta is the same, given the setup of the question. A is also the same, at least for now. They've got access to the same production technology. They also have the same alpha. Therefore, we know that for these two different economies to converge to the same steady states, their savings rate have to be the same. And because of the diminishing marginal product of capital, yes, Durpistan will grow faster. Actually, I believe it's Chirpistan. Durpistan, will grow faster, but it eventually slows down and converges to the same steady state that Chirpistan is going to reach. So in the long run, they're going to reach the same steady states. They're just starting from different points. Okay, so let's return to both countries having an equal endowment of K equals 12,000 and L equals 10,000. Suppose Durpistan's population goes into heat and, they make babies, right? They get some kitties. Chirpistan doesn't. No kitties for them. Durpistan's labor force increases by 2,000 because, their population went to heat and they had babies. What is the output for each country now, and which country's got greater output? Well, here we know output for Chirpistan's 10,626.59. For Durpistan, however, it's going to be 12,000. So we've got our total outputs, right? 10,626.59 and 12,000. But now we need output per worker. All right, this is where it's going to get really interesting. So we take total output and we divide it by the population. Here we can see Chirpistan actually has higher output. Chirpistan's output is 1.062. Durpistan's is just 1. All right, so even though Durpistan's production is higher, per capita income in Chirpistan is higher. So now from that previous question, what's the relationship between population size and output per worker? Well, we can see output per worker falls with an increase in population. Why is that? Well, if we hold K constant just for now, and we increase labor, L, the amount of capital that's available per worker will fall. We got fewer units of available capital for each worker. And if capital per worker falls and output's a positive function of capital, then output per worker will also fall. Conclusion time. So this wraps up Chapter 7. So we covered the Solow model, how to solve it, what it means. And really, one last question we talked about here, at least a little bit. Did the model fit the data? And the answer is sort of. It leaves a lot out. And the results of some tests indicated that, total factor productivity was abnormally larger than what it should be, right? Which means that technology is increasing at a stupid high rate, which isn't the case in the real world. So the model didn't fit the data all that well. We need a new model to explain it. Neoclassical growth model actually was one of the models that came after. That's sort of like the workhorse model for stuff like this now, which included optimizing households and, really actually improved some things a lot. And then that neoclassical growth model really leads into business cycle stuff, which is what we'll be talking about in the next section of this course. That said, this actually wraps up the first section of this course, and we will begin business cycle theory a little bit later. So, with that said, the exam will be coming up soon. I will be announcing the exam, and probably assigning another homework just to give you guys some extra practice before the exam. So with all that said, thank you for watching this video lecture. Hopefully, thank you for watching the entire section thus far, and looking forward to seeing you in the next.